Hello and thanks for listening. Let me begin by stating what we are trying to achieve. We wish to develop pairs of indicators which behave more or less like the ones in the graph. In this case, the blue line leads the red one by a number of months over a long period of time. Our project aims to make available R scripts for developing systems of cyclical indicators. By updating and improving upon current practice by national and multinational agencies, and by updating prototype routines originally written in Fortran 77. From the beginning, about a century ago, development of cyclic indicators followed the 5 steps depicted in the slide. In this presentation, we shall concentrate on the one squared in red. Without regard to any optimality criterion, the growth rate of the composite index is obtained as a simple average of the growth rates of each of the component series. The blueprint of our full proposal is shown in the present slide. For the sake of brevity, we shall concentrate in the colored square. For each harmonic series, the spectral matrix is partitioned according to the number of coincident and leading indicators. They will help us determine vectors A and B of coefficients. They can be obtained as a solution of an optimization problem. It can be proven that they can be obtained as eigenvectors of appropriate matrices. Vectors associated with the largest eigenvalue give the solution to our problem. Our proposal has been implemented in Fortran and R codes. Both have been used in a number of Mexican time series in order to evaluate their performance. The eigenvalues obtained by using the Fortran code are shown in the current slide. In it, P1 stands for the first canonical pair of composite indicators. They can be seen to be roughly the same as those obtained using the R code. The first and second pairs of composite indicators using the Fortran code show a behavior which is adequate. Sadly, this is not the case for the R code, as can be seen for the graphs in the present slide. On the other hand, while the first pair of composite indicators shows a larger correlation than that shown by the traditional procedures, the corresponding pair obtained using the R code is somewhat disappointing. We think that one of the main reasons for the differences exhibited lies in the different routines used for eigenanalysis. Both routines are based on LAPAC, and we have seen that the eigenvalues are roughly the same. However, the eigenvectors are not in general, and we think that that is because eigen imposes identifiability conditions in the form that the first component of each eigenvector is forced to be a real number, whereas for the IMSL routine, the largest modulus entry is the one forced to be real. Both sets of conditions provide an equally suitable spectral decomposition of the spectral matrices. However, the representation of the indicators is not necessarily the same. So, as has been shown, results may differ and may differ widely. This leads us to pose a more important question regarding a better set of identifiability conditions, one in particular that will preserve optimality in the frequency domain for the time domain results.